Okay, so topic 4 is focused around bonding and the types of bonding. And so what we'll do first is we'll establish um, the types of bonding and define them, and then we'll kind of dig deeper into covalent bonding and its characteristics and its how to draw Lewis structures, and then we'll talk about how that translates into shapes and things like that. I'm going to save naming till maybe the end of the SL if we have time. I think most of y'all are pretty comfortable with naming, but just a little quick reminder if we have time at the end for naming. But so um, the first thing we want to talk about is ionic bonding. Okay, and ionic bonding is the electrostatic attraction between oppositely charged ions. Okay, so the idea here is that you have species that have gained and lost electrons that have become positively and negatively charged, and that attraction creates the structure that's provided here, the bonds in this ionic structure. And so, because ionic bonding is fairly strong, most ionic compounds exist as a solid lattice. Okay, lattice is another kind of term for crystalline structure. It's a fixed repeating pattern of these ions. We don't need to go into the specific types of crystal lattices, but that's the kind of main idea here. Okay. Along with ionic bonding, you have to know specific polyatomic ions that you need to be familiar with. So just a reminder, these are the polyatomic ions that the IB holds you accountable for. So write this here. Any other ions, if they're involved in the test, they will have to give you information regarding them. Okay. So ammonium is NH4 plus. Okay. Hydroxide is OH minus. Hydrogen carbonate or bicarbonate, either term is acceptable, is HCO3 minus 1. Ethanoate or acetate is CH3COO minus. Nitrate is NO3 minus. And cyanide is CN minus. Those are all the one negative charges of polyatomic ions that you need to know. The 2 minus ones you have to know are carbonate, which is CO3 2 minus, sulfate, which is SO4 2 minus, dichromate is Cr2O7 2 minus. That one you will see in organic chemistry. When we talk about oxidation reactions, you'll see dichromate show up. So there is a purpose for dichromate being here because it seems kind of um, weirdly included in all these things. And last but not least, we have phosphate, which is PO4 3 minus. Yeah. So these are the 10 polyatomics that you are held responsible for in the IB exam. And so if they name a compound that involves these, it is assumed that you can write the structure out. Yes, Doris. CR2. Sorry, CR2. Let me write it more clearly. Dichromate meaning 2 chromiums. three major physical properties that we have to talk about in ionic compounds are as such. Volatility, and we're going to define each of these terms before we kind of apply this. And so you have to make sure that you understand volatility in kind of chemistry context is different than kind of what you imagine it in the English kind of vernacular. And so volatility here has nothing to do with actual explosions and that. All it means is the ability to evaporate. Okay. And so the ease at which it evaporates. And so things like gasoline, acetone, those evaporate very quickly. They're very volatile. Now, it happens that when they evaporate, they become flammable and they combust, and that's what's dangerous. But the volatility itself doesn't have to do with how flammable or combustible it is. And so with ionic compounds that have the strong ionic bonds, you have low volatility. And we'll revisit these characteristics in covalent compounds as well, or molecules. So volatility is ability to evaporate. Electrical conductivity. Okay. The ability of electricity to pass through a substance due to free moving electrons or ions. Okay. And that's the key thing here. Bless you. When you talk about electrical conductivity, you want to talk about, does the species have free moving electrons or ions? And make sure you use the right one in the right context. So if you're talking about ionic compounds, to conduct electricity, it has to have free moving ions. If you're talking about metals, then you have free moving electrons. So make sure you're using the right context here. And this connects back to electrolytic cells. If you remember in oxidation reduction, like when you, bless you, when you do electrolytic cells, you put electricity through molten ionic compounds, you have to have it molten because solid ionic compounds don't conduct electricity because all the ions are fixed. And so if we're doing this, we're going to talk that in a solid ionic, you have no conductivity because you have fixed ions. In the molten or liquid, aqueous, or gaseous, you have high conductivity because of the abundance of freely moving ions. Okay. And so once you melt it down, you've broken enough ions apart that the ions are able to move freely. And that's what the liquid state really is. And so not all the attractions are broken, but enough of them are broken that it's not a solid crystal lattice anymore. It is able to kind of freely slide across each other in that state. Aqueous is another idea. Aqueous water surrounds each ion and breaks apart the crystal lattice so that the ions are separate enough that electricity can pass through them. Okay. So characteristics here, an ionic compound should never conduct electricity in the solid state, but should always conduct electricity in the liquid, aqueous, or gaseous state. A kind of common question that they'll do in multiple choice is they'll list characteristics of an unknown compound and ask you to identify is it ionic, metallic, or covalent. And these properties are the ones that distinguish them apart. And we'll kind of collate all these into a chart in a little bit. The last characteristic that we're going to focus on is solubility. And for our purposes, we're going to focus on solubility in water. Okay. Now, we don't need to know all the solubility rules. We don't need to know like which ones dissolve or not. And so the idea here is you just want to focus on the idea that ionic compounds vary in solubility based on the ions present. Because what solubility is the idea that the water molecules are polar enough that they can separate the two ions that are in a compound. And so for solubility to occur, the attraction to water has to be greater than the attraction to each other. So the idea is that it has to be more attracted to the water than each other, and that's what allows water to separate the ions and make it dissolve. So things like sodium chloride, the attraction between the water and the chloride and the water and the sodium ions is strong enough that they're able to break that ionic bond and surround themselves with water so that they can't reform those bonds. But in something like silver chloride, a precipitate, the bond between silver and chloride is so strong that water cannot cleave it, can't separate those atoms and pull them apart because they're attracted to each other more than they are attracted to the water. So for solubility to occur, the attraction has to be the water. Okay. On a side note, make sure that you're discussing ions in the correct name. Anytime you have an anion, like chlorine's negative ion or bromine's negative ion, when you're saying the ion name, it's the "ide" version. So you don't say a chlorine ion, you say chloride ion. So chlorine, yeah, so you say the chloride ion, but you say the chlorine atom. It shows you don't necessarily understand the naming, because really what naming is just naming each ion and then putting it together. So like NaCl is sodium chloride because it's a sodium ion and a chloride ion, and you just take the rid of the word ions and put it together. That's all naming is. So make sure you're calling it the chloride ion and not the chlorine ion. I don't know if that's enough for them to mark off a point in your explanation, but it does show a lack of understanding of the difference between those two things. So the chloride ion and versus the chlorine atom. Questions about these three characteristics? We're going to apply these properties to all three different types of bonding that we're going to talk about today. Okay, so we'll do metallic bonding next, even though it's not necessarily in that order, and then we'll go back to covalent because the majority of this topic is about covalent bonding. That's just kind of the nature of this. So metallic bonding. Oh, let me scroll down in case you're. Okay, metallic bonding is the electrostatic attraction between positively charged ions and delocalized electrons. So metallic bonding usually generally are having a metal species that donates all of its valence electrons to the entire substance, and then that delocalized those delocalized electrons hold all the positive ions together in a lattice. Okay. And the strength of a metallic bond is dependent on the charge of the metal, the charge of the ion, and the radius of the ion. if you look at the periodic table and the melting points, you can kind of see that relationship here. And so I'm going to flip back to that and show you what I was like. In the data packet, they have a periodic table just dedicated to boiling points and melting points. So sorry, it's sideways, but you can see the melting point for these metals decreases as you go down the group, okay? And so that tells you that even if they all have the same charge, the radius has an impact on that. And so going down a group, the larger the radius, the weaker the attraction it has for the electrons. And as you go across, it increases. And so therefore the increase in charge increases the attraction between the species. And so you'll say that you want a smaller radius and a larger charge for a stronger metallic ion. That's a general kind of concept here. So understanding that with melting point. Other characteristics of metallic bonding, they have strong electrical conductivity due to its free delocalized electrons. So strong electrical conductivity. Also, they are malleable, which means able to be hammered into thin sheets. And also ductile, which is pulled into wires. Sorry, let me move that up. Okay. The reason why this is because the metallic bonding lattice is not a fixed one like it is in like sodium chloride, like an ionic compound. The lattice of the positive ions is able to kind of move freely along with the movement of the electrons. So when you hammer a sheet of metal, the ions and the electrons just start spreading out further and kind of further and further apart until there's like only a few layers left. And so that gives it the flexibility to be able to be hammered into thin sheets or kind of drawn out like long wires because the metallic lattice is much more adaptable. It's much more free flowing. Okay, one more thing about metallic bonding before we move on. Alloys, okay? An alloy is a mixture of addition of an element to mix with a metal. So, how do I want to do this? Into metal. Okay, so it is a kind of a mixture. It is, think of it kind of like a solid solution. You're dispersing this additional element throughout the metal lattice, and it gives it different properties. Okay, things like steel. Steel is an alloy. You have iron, and you mix in carbon or graphite with it to give it different properties. Okay. Now you don't have to know the specific types of alloys like interstitial versus like substitution alloys, I don't believe, but interstitial means like it's a really small element that fits in between all the cracks of the large metallic ions. So like it fills in the little gaps. Like carbon's a really small atom. And so the way iron's distributed, the carbon fits in the little cracks between all of the different iron atoms to give it more strength. A substitution alloy is exactly what it sounds like. Instead of having like copper, 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 you do copper, zinc, copper, zinc, copper, zinc, and that makes bronze. Oh, brass. I always forget which one's brass and which one's bronze. Brass is with zinc, bronze is with tin. Okay. But so the addition of an element to the metal changes the metallic lattice. And usually it makes the substance harder, which is less malleable or ductile. Because the introduction of this other element into the substance affects how mobile the positive ions can be, which sometimes can be a good thing, sometimes can be a bad thing. Steel comes in a lot of different mixtures. You can change the percentage of graphite to see what kind of steel you want. Do you want a more flexible steel, or do you want a harder, more rigid steel? Okay, a flexible steel has kind of the ability to be shaped more. A harder steel can withstand brunt forces much more, but once it does overcome that force, then it just kind of breaks. It doesn't have that flexibility. I don't think we need to know all these examples. I'll write down a couple examples so just in case. So brass is mainly copper with zinc added. Bronze is copper with tin added. And steel is iron with carbon added. So just a couple of examples of what alloys are. I would say the substitution ones with bronze and brass and bronze are maintain more of the metallic characteristics. When you get interstitial ones where you're putting atoms in between other atoms, like the crevices and things like that, that makes it more rigid, but then doesn't allow the iron atoms to move as freely. That's what steel is. Okay. Questions about that? Kind of all conceptual stuff right now. Okay. So, does everyone have that? Okay. So the main aspect that we have here, oh, you know what? Let me mention something here too, because sometimes this comes up. But usually, metallic bonding has slightly lower melting points than ionic bonding. So if you're trying to figure out which one's metallic and which one's ionic, usually metallic ones have slightly lower melting points than ionics if you're trying to figure out a tiebreaker. Some of them are drastically lower, but usually ionic bondings is stronger than a metallic bond when it comes to trying to melt it. So just kind of a note, because I've seen that on multiple choice. They'll have like an unknown compound, and like they'll both be conductive and liquid, and one will have like a melting point of 300 and one will have a melting point of 1,000. Well, if you had to choose, the one with 300 is probably your metallic bonding, and the 1,000 is probably your ionic bonding. Okay, so covalent bonding. Okay, again, defined as starting with electrostatic attraction between, let's see, how do I do it? Between positively charged nuclei. Notice that I'm saying nuclei instead of ions, and shared electrons. So be careful, because that's the only difference between all the types of bonding. It's what species are interacting with each other. Is it two oppositely charged ions? Is it a positively charged ion and delocalized electrons, or is it a positively charged nucleus and shared electrons? So be careful about that wording in this. Okay. Now, for covalent bonding, you can form single, double, or triple bonds. You cannot have a quadruple bond. It's not physically possible with the way the orbitals are aligned to have a quadruple bond. Okay. And one thing I want you to understand is that um, that that how do I want to say this? A double bond, yeah. Well, so when we start talking about orbitals, you'll see that because if you think about the way the orbitals are all lined up in the x, y, and z, and then the s orbital, you can't ever have four different orbitals lined up right across from each other. Yeah. So a double bond is stronger than a single, but not 2 times stronger. So what you have to understand is that when you add additional bonds between two atoms, they're stronger, but it's not twice as strong because that second bond you add for higher level is called a pi bond instead of a sigma bond. It's a parallel overlap instead of a physical overlap. Yes, Theodore. No, you do not. Okay. So yes, that is an HL concept with pi bonding and sigma bonding. Okay. But so you don't have to memorize this because you can see this in your data booklet. You see all the different bond enthalpies in your data booklet, and you'll notice that like a carbon a carbon I don't remember off the top of my head. I think carbon to carbon is 414, but like a double bond is like 6 something, and so it's stronger, but it's not double that because they're not the same type of bond as you're adding more and more bonds. So, having said that, that relates to bond length and bond strength. So we've established that a triple bond is stronger than a double bond, which is stronger than a single bond, and that stronger attraction pulls the nuclei closer together. So in the bond length, the triple should be shorter than the double, which is shorter than the single. Okay. And so understanding that bond length and bond strength kind of establishes a few things that we'll use to prove concepts a little bit later. Okay. Questions so far on the types of bonding and the kind of characteristics of bonding. Because what we're going to do next is I'm going to show you how to do all Lewis structures. Okay, whether SL or HL, if you do it in this way, you will always get the right structure. Now, like I've said, sometimes it may feel that it's longer. It takes longer than other ways to do it, but it always works. So then you don't have to memorize, oh, if I just pair electrons when it's less than 4, or I do this when it's more than 4, why do 2 things when you can just do one thing consistently? You know, minimize what you have to memorize. And it's going to feel a little bit like trial and error, but there is a method to this. Okay. And so we're going to talk about drawing Lewis structures. Okay. So here's what you need to know when you draw a Lewis structure. Okay. And I'm going to give you an example that you all know right away, but so that way you don't have to think about it. You can kind of just follow the process. Okay. CO2. Okay. let's say this is something that we don't know, and this is what we have to do, okay? The idea is this. Anytime you draw a Lewis structure, you are limited to how many electrons you have available in your compound, okay? And that allows you to do things, and it restricts you from doing other things. And so this is what I tell people to do, okay? What you do is you calculate what I call the math number, which represents how many electrons are available, okay? So with the math number, and I'm going to use that term kind of throughout this, I just calculate all the valence electrons in all the species. So carbon and 2 oxygens means 4 plus 2 times, bless you, 6 is 16 electrons, bless you, divided by 2. Okay, I'm going to have to stop. 8 pairs. No, it's okay. Okay. So you have 8 pairs of electrons to work with. So I divide my number of electrons by 2. As a note, if you have a negative charge, that means you add electrons. If you have a positive charge, you subtract electrons from your total. So if this were an ion, you would have to incorporate that into your math number as well. So our math number here, bless you, is 8 pairs. So in my final structure, I'm only allowed to have 8 pairs of electrons. Okay. What I do next is I draw a test structure. Okay. A test structure in my definition is defined as the structure where all atoms meet their electron needs with single bonds. Yes. Oh, so let's say you have something like F minus, right? F would normally have 7 valence electrons, but with a negative charge, that implies there's another electron from another source. So then it would be 8 electrons. Yeah, so I'm adding electrons, and we'll do some examples of that as well. Okay, so the structure where all atoms meet their electron needs with single bonds. Okay, now what I want you to make sure you think about is that this is all theoretical. So this structure doesn't have to be possible. Like, this structure isn't always the right structure. It's a starting point. It's the most basic way you would draw the structure, and then you change it to make it match what you need. So this is the simplest of the simplest structures, and then you add bonds and add things to make it match your math number, because it has to match your math number. And a couple rules here, okay? If an atom has 4 or more valence, it must have an octet in this test structure. I don't care if it doesn't look right, you have to give it an octet, because every atom that has 4 or more is going to try to get at least an octet. If it's less than 4, then you just go with whatever bonds it has. So like, for example, hydrogen has 1, so it should only have 1 bond. Beryllium has 2 electrons, so it only has 2 bonds. Boron and aluminum should only have 3 bonds. So if it has 4 or more valence electrons, make sure it has an octet in your test structure. So with CO2, C's in the middle, and I make it as simple as possible. So that's the structure that, if everything was as basic as possible, that's what it would look like. Okay? I'm not saying it's right. I'm saying it's our foundation. Okay? And I look at that structure and I count how many pairs I have. Okay? So here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pairs. So in this structure, I have 10 pairs. But I can only have 8. So what does that tell me about some of these lone pairs that each atom has on their own? What do they actually have to be? Bonds. because instead of each of these atoms getting their own pair of electrons, they're actually sharing one pair, and it represents kind of like this in a bond. So here's what I'm saying. Let me say that again. This structure is everyone having the maximum electrons to themselves, but that's not always the right structure. So these two pairs aren't by themselves. They're really one pair in between, and they both get to count them as a pair of electrons. And then these two aren't by themselves. They actually count as a pair here. So because you have 10 pairs and you need 8, you have to add 2 bonds in your structure and replace some of those lone pairs with bonds. So what I'll do is I will take away these 2 pairs, draw this, take away 2 pairs, and draw this. So my overall structure is this. So I did my math, and I did my test structure, and I had to make them match. And whenever you have more pairs than you should have, you have to add bonds. So if my structure here has 10, and I'm supposed to have 8, I need to add 2 bonds. Maria. Okay. Nessim. Oh, this structure here has 10 pairs. Like this test structure method has 10 pairs of electrons. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That doesn't work. So we have to manipulate this structure to make it fit 8. And the way we do that is we add bonds. And that always works. Okay. Now, I know some of y'all would just say, oh, I can just write C with 4 dots and O with 6 dots, and I'll just pair my unpaired electrons. And yeah, that works for that situation. But then what happens when you get into carbon monoxide? You try pairing electrons with carbon monoxide, it won't work. It's just not physically possible the way you draw things out. Because carbon needs 4 bonds and oxygen needs 2 bonds. And so how's that going to work? So we do the same thing that I'm going to do here. So carbon has 4 and oxygen has 6. So that means my structure, my final structure, can only have 5 pairs of bonds. That's it. But I draw my test structure. Single bond, everything with octet. How many pairs do I have here? 7. I need 5. So what do I have to do? Mofe, add 2 bonds. So I replace all those lone pairs with bonds instead. So now this becomes 3 bonds and 2 lone pairs. That's the structure of carbon monoxide. Yes, Tamor. Okay, see, this is why I do it this way, because there are exceptions to every rule. And if you do it this way, you fit in all your exceptions. Tamor brings up a good point, because oxygen shouldn't have 3 bonds, but in this structure it does, because that's the only way it works. So that kind of leads us into a little bit. That third bond here is not an equal sharing. It is actually a dative covalent bond, where one atom gives both electrons to form the bond. So usually you write it like, let me redraw it. So usually you write it as an arrow this way to show that oxygen is donating both electrons. But if you did dots, you would never see that. You wouldn't see that one of those bonds has to be both electrons from the oxygen. So that's why you do it this way. It always works. All exceptions, everything like that are factored in. So a dative covalent bond is when one atom shares both electrons. And in HL, you see that in complex ions. You see that with ligands bonding with metal ions. But SL also has to know what a dative covalent bond is. And so I would say the rule of thumb is a dative covalent bond happens when an atom bonds more times than it should bond. So like Tamor said, if you see an oxygen has 3 bonds on it, there's a dative covalent bond there. If you see a nitrogen with 4 bonds, when it usually only wants 3, that's a dative covalent bond. Questions? We will do more practice. This is going to probably take the large majority of what the SL's rest of the time is, because there's also another great thing about this. I wouldn't say great, but a useful thing. Yes. Okay. Now, yes, Doris. If it states it in the question, yes. If they say include any dative covalent bonding, you would draw an arrow there. But usually I don't think they do. Melvin. Thought I saw your hand up, Melvin. Okay. So what's great about this is, one, it incorporates dative covalent bonding, which is exceptions that you normally wouldn't see. The second thing is ozone. Okay. O3. Okay. If you do the math for O3, it's 9 pairs. But if you draw out O3 in its actual test structure, how many pairs are there? 10. So what do you have to do? Add a bond. Question is, where do I add the bond? That's the question. Does it really matter where I add the bond? Left or right? Doesn't matter. Guess what this represents? Resonance. So if you do it this way and you go, I have to add a bond, but it doesn't matter where I add the bond, that's resonance. So this technique incorporates resonance and dative covalent bonding. So what this tells me is adding one bond means resonance. So if I do the structure and I go, I have to add a bond, but it doesn't matter where, it ends up being resonance. And so this ends up being, it could look like this, or this. And you have to show both of these generally if you have it. Yes, Mofe? Okay. Yes, Melvin. Well, okay. That's a little bit different. The concept of what you're saying is that if we labeled each atom, if you flipped it, it wouldn't matter. But here, the double bond is actually on a different oxygen. So this is not a mirror image of it. It's like, let's say this is oxygen number 1, oxygen number 2, and oxygen number 3. In this structure, oxygen 1, 2 has a bond. In this one, oxygen 2, 3 have a bond. Mepsim. Technically, Mepsim asked, can you draw a dotted line? I don't like the dotted line for this reason. Because if you draw the dotted line and then you have the wrong number of lone pairs on each of it, it's wrong. So generally speaking, the IB wants you to draw resonance in all the possible states like this. So I would draw it like this. Yes, Doris. I wouldn't, because like I was telling Mepsim, if you do that and you get one of the lone pairs wrong on one of the terminal atoms, then it's all wrong. So like if you do the dots and then you forget that each one only gets like the least number of electrons that it should have in resonance, then it's all wrong. So I think the IB doesn't want you to do dots. Okay. Okay. Now, we're going to do some more practice, but the way scientists figured out that this was resonance, the reason why we know it's resonance is because when you experimentally, both O to O bonds were equal length. So when scientists measured how long the bond lengths were, they found they were both the same. And if they're both the same, then one can't have a double bond and one can't have a single bond. They have to be sharing that double bond somehow. And that's how resonance, the concept of resonance came up with. That's how it was evolved. It was kind of reasoning based on the experimental data. So the way you prove that resonance occurs is that you measure the bond lengths of this, and the bond lengths are the same. Which also adds another concept, which is called bond order. Okay. Bond order is essentially the effective number of bonds between atoms. And so the way you do that is you take the total bonds divided by the number of atoms bonded to center. So it's the total number of bonds between all the atoms divided by the number of atoms that are bonded to that center. So for ozone, there are 3 bonds total, and there's 2 atoms of oxygen bonded to the center. So the bond order for ozone is 1.5. And we're going to keep doing this. Now, this only matters when you're really doing resonance, because in all the other ones, when there's like only one like type of bond, then it's always that's the same bond order. So like in carbon monoxide, the bond order is 3 because there's 3 bonds between 2 atoms. So 3 over 1 is 3. So it's easy when it's just like one type of bond, but when you start having resonance, you'll start getting decimal bond orders. And that relates to the strength as well. So a 1.5 bond order fits in right between a single bond and a double bond. It's somewhere in the middle. Mofe? Yes. Oh, atoms. So like here, ozone, there's 3 total bonds, and there's 2 oxygens bonded to the central atom. Yeah, sorry. Oh yeah, no. Center atom. We're going to do quite a few of these because I think it's really important that we understand what this is. Questions about what we've done so far? What's great is when we talk about higher level, this works for higher level expanded octet too, because oftentimes you don't see the additional lone pairs on the central atom when it expands, but this way you will, because your numbers won't match and you'll have to add more pairs. So it always works. Yes, Tamor? It's because last year in 11th grade, to make all the content work, we have to incorporate some higher level in there. And so since no one's officially decided what level they are, we incorporate some of the higher level into that year to help people make a more informed decision on kind of where they stand. I know some people already know their SL, but sometimes students are surprised by their ability to do it, and sometimes they switch classes at the end. And so we incorporate a lot of SHL into the 11th grade year for 2 reasons. One, because sometimes kids change their mind. And 2, some of the fundamental stuff that's HL in the first like 5 topics, everyone should know. Like just fundamentally, if you're taking any general chemistry class in college, you'll see those things. And so we incorporate that in there. And even if you're SL and you have to take the SAT too, you have to know all that HL stuff too. Yeah. Okay. Let's look at another example of this. Okay. CO3 2 minus, carbonate. Okay. First thing I do is math number. Okay. Carbon, 3 oxygens, and a 2 minus charge. So that's 4 plus 3 times 6 plus 2. So that's 18 plus 2 plus 4 is 24. And that is 12 pairs. So I need to know my final structure can only have 12 pairs. Because the carbon donates 4 valence electrons. Each oxygen donates 6 valence electrons. And the 2 negative charge implies that it got 2 electrons somewhere else. So we have to factor that into our so my total structure should have 12 pairs. Now, my test structure draws everything with an octet because all these have more than 4 valence electrons. Because so 4, these have 4, so all these should have an octet. If it had less than 4, then you don't worry about the octet. But if it has 4 or more, you have to worry about the octet. So that's my test structure. Yes, Mepsim? No, it doesn't. That's a good question. The orientation of your atoms doesn't matter. Like, they're not going to grade you based on the shape of your Lewis structure. I get into habits of drawing it in the correct shape, but that's not important. Okay. So how many pairs are on this structure? 13. So that means you have to replace 2 lone pairs with 1 bond instead of 2 lone pairs. So you're replacing, make sure you understand, you're replacing 2 lone pairs with 1 bond. That's what you're doing here. You're not just adding a bond on here. You're replacing 2 of these lone pairs with a bond so that everything's still happy, everything's still complete. Okay? Does it matter where I add the bond? No. So it is resonance. And in fact, how many resonance structures does this structure have? 3, because there are 3 different places you can add that bond. So what you get is, one structure where it looks like this, and you have to write the charge. So this is 2 minus, and then one structure that looks like this, and one structure that looks like this. So carbonate, which is CO3 2 minus, has 3 resonance structures, and they'll ask you to draw all 3. They'll say include all resonance structures. Yes, Ginevra. No, that's just me in a habit of doing it because, like, I see the shape of it, and so when you have this, we'll talk about shapes. This is a trigonal planar shape. No, they will never grade you on the way you draw your Lewis structure. So you could draw it as a T if you wanted, and that'd be fine. Huh? No, you're not graded on like how you draw your Lewis structure. You should be able. It helps you identify the shape, but you're not graded based on how you draw Lewis structure. As long as the right bonds and lone pairs are right, it doesn't matter. No, you do, but you don't have to represent them in your structure. That's what they're asking. They're saying, if I know this is trigonal planar, do I have to draw it as a Y? No. When I draw water, I don't have to draw it as bent. Yes, it would be a separate question. They just ask you to identify the shape. They wouldn't expect you to draw this in that shape. Okay. Okay. Let's see. Oh, I thought I heard a question. Okay. Let's see. Oh, so bond order here. Okay. So how many total bonds do we have in this structure? 4. Because there's 4 bonds between all the oxygens. I got to be careful about that. And how many oxygens are bonded there? 3. So this bond order is 1.33. That tells us the strength. So a 1.33 is slightly stronger than a single bond, but weaker than a double bond. And actually, it's closer to a single bond than a double bond because it's less than half. So this is just helping you to relatively organize them. So like if they gave you, I don't know, a C to single bond O, a carbon dioxide, and this, this bond order of 1.33 would be between the 1 and a 2 if you're ranking them. Okay. Let's see. Something like BF3. Okay. This one, students get a lot mixed up because they forget that B has less than 4 valence electrons. So the math number is B and F3. So that's 3 plus 7 times 3. So that's 24 divided by 2. That's 12. So then your test structure looks like this because you don't have to have 8 on B because it has less than 4. So you leave it alone. You don't put lone pairs on there. And when you do that, how many pairs do you have here now? 12. So you're done. So math number, test structure. If you do it this way, you should never get the wrong structure. You should not have to worry about resonance or dative covalent memorization because it's all incorporated into this style. Yes. Oh, bond order kind of tells you the relative strength of the bond. So bond order of 1.33 tells you it's a little bit stronger than 1, but a lot weaker than 2. So like if we're looking at bond strength here, let's just say like if it was a spectrum, right? Like if this were a single bond and this were a double bond, then this one, it would be kind of like here in the strength, 1.33. That's the way you think about it. Oh, because remember how I said earlier bond strength relates to bond length and stuff like that? I've had IB questions before where they say, here's 3 different molecules with a CO bond. Rank them in bond length. So then you would have to rank, bless you, you would have to rank this species with this bond length, bless you, as greater than a double bond, but shorter than a single bond, because it's stronger than a single bond, but not as strong as a double bond. So just use this to kind of help you relate any properties that have to do with bond strength. Okay. Questions on that? Okay. Okay. Next, we're going to do shapes. Okay. And we're just going to focus on the SL shapes right now. We'll incorporate the HL shapes with the addition of expanded octet after SL's done. But since y'all have seen shapes before, okay, I know you haven't like remembered all the shapes, but I'm going to show you how I remember the shapes. And there's kind of a method to the way I do it. Okay, so you've already seen shapes, so I'm going to kind of go through this a little quickly, but then I'll show you how I remember it. Okay, now, sorry, does everyone have this? Okay, so, okay, electronic geometry and molecular geometry, we need to define those concepts. Okay, and so electronic geometry, okay, it is the shape around all electron pairs. So that means that every lone pair counts as a bonding pair in the shape as well. Okay, so for SL, there are only 3 electronic geometries that you can possibly have. Because lone pairs count the same as bonding pairs. Okay, HL it's just 5. It's not that much more. It's not like 12. Okay, everyone thinks that it's going to be like a lot more. Molecular geometry is a shape around the bonding pairs. So now the lone pairs matter. They change the shape around the bonds. Now, if you don't have lone pairs, then these are the same. But if you have lone pairs, that affects the shape. So electronic geometry and molecular geometry could be the same, but they could be different as well. So for SL, you would need to know, I guess, the 3 electronic geometries, because they could be molecular. And so you need to know 6 molecular geometries. That's including the 3 electronic. Okay. No. The 3 are already in the 6 table. Because there's an overlap. There's an overlap of molecular and electronic geometries. So it's just 6. So, sorry. Here's how you do it. Okay. What you care about here is, the way I do it is this. Okay. You have, yeah, sure, right there. The purple. Yeah. So you have bonding pairs and lone pairs, and then charge centers, which is the sum of those. Okay. And then that leads us to our shape. Okay. So if you have 2 bonding pairs and 0 lone pairs, you have 2 charge centers, and that is linear, which is, because it's a straight line, 180 degrees. Sorry if you can't, let me write that a little bigger. 180 degrees. Charge centers. So a charge center is either a lone pair or a bonding pair. Okay. If you have 3 bonding pairs and no lone pairs, it's called trigonal planar, which is that Y shape that some of y'all were talking about earlier. And when you have a Y shape, the angle here is 120 degrees, because you're essentially breaking up a circle into 3 sections. So each angle is 120 because the circle is 360 degrees. Okay. I'm going to do all the electronic geometries first. I'm going to do a little bit differently than I normally would. But so 404 is tetrahedral. That's the best you can draw in 2 dimensions, but that still will help us here. Tetrahedral, because you're using 3 dimensions now, is about 109.5. You could just round to 110, that'd be okay. It's not exactly 109.5. Like the IB will take a range of angles. They could say 109 to 111 is acceptable. So 109.5, 110 is fine. Okay, so that angle is between all the different species. So when you make the structure of all 4 atoms bonded to it, every angle between each of them is a 109.5, because you're in 3 dimensions now, so you have more than 360 degrees of freedom. So that's why it becomes 109.5 instead of 90, which is the logical. Yes, Olivia. No. Okay. Valid question. I don't have an answer, and I'm not going to repeat it. Okay. So these are my 3 electronic geometries, because notice the lone pairs aren't in there. Okay. And so these, if you have this number of charge centers, that's this electronic geometry here, no matter what any other combination is. So keep that in mind, because we're going to do some of the lone pairs now. Because if you have 2 lone pairs and 1 one lone pair and two bonding centers, you still have three for your charge centers, which means your electronic geometry is trigonal planar, but your shape is bent because you have that lone pair up here now. Okay. Now, because that lone pair is pushing the atoms close to each other, because the lone pair has a lot of repulsion, the angle gets smaller. And the angle gets smaller by about 3 degrees. I think your rule of thumb is every time you have a lone pair, just subtract 3 degrees and you're safe. So this is 117 degrees. That's a reasonable number. But the electronic geometry still is trigonal planar. Just keep that in mind. But the molecular geometry is bent. Yes, Ginevra. Yes. And these two numbers signify the molecular geometry. Exactly. Here, let's say we have 3, 1, and 4. That's still tetrahedral, but because you have a lone pair now, you have trigonal pyramidal. So now you have a lone pair, but you still have a pyramid down here, kind of a tripod. It's hard to draw on paper, but imagine it like a pyramid. And sorry, so imagine it kind of like my fingers are here, Diana, where it's going to be three-dimensional. So the angle here, just subtract 3 degrees. So it's about 107. Okay, because it starts at 109.5, lone pair 107. 106.5 is fine too. I would say 2 or 3 degrees of leeway, but you have to make sure that 2 or 3 degrees doesn't overlap with a different shape. So be careful about that. That's why I just say take the electronic geometry and just keep subtracting 3 degrees for every lone pair. So let's say we have 2, 2, and 4. Still tetrahedral, but now we have a different bent because now we have these two and two lone pairs up here and here. Okay. And that angle, I know, they're starting to look like faces, I know. Okay, this angle is not 107, it is 104, 104.5, which is a bent. It's a different bent, so make sure you keep that kind of separated. Okay. That is the last shape. Now, let me show you, like here? Okay. Now, I have a trick to this as well. And now you may not all like this, but it's something that you might be able to use in case you kind of get stuck. Okay. I drew these lines up here this way on purpose because that's how I tell kids if they're struggling with shapes to remember these shapes. So what I tell them to do is this. Draw all your electron geometries out in line form. So for example, linear, trigonal planar, and tetrahedral. Can I move it up a little bit, Maria? Here? Okay. Draw these out. Okay. And what I tell them to do is this. Every time you have a lone pair, cover up a line because that line is now gone. And that gives your molecular geometry. Because look, trigonal planar. Why? Lone pair, what's left? Bent. It's visually there. Tetrahedral, cover this up. Pyramid, cover up another one. Bent. That's how you remember it. Just visually, if you draw these three structures out, just cover up lines and that's your shape. HL, it helps a little bit more because it's a little more complicated. But even for SL, you save yourself having to memorize 3 shapes by just covering up lines and making shapes. So Just remember your 3 electronic geometries. Everything else sorts out. Yes, Mepson. Doesn't matter, right? Because like I guess visually it's hard to see in 3 dimensions. So I think what I usually do is I always cover the one pointing up first. So Mepson asked a good point. Yes, when you're drawing tetrahedral, it's hard to see the pyramid if you don't cover the top one. So when I do this, I cover the top line first, and then I do everything else after that. So that's a good point, Mepson, because tetrahedral is hard to see in 3 dimensions. So cover the top one first. Yes, Catherine. That's HL. And you'll see that when we get into HL shapes that this works as well. Okay. Questions about... You all right, Mofe? No. Okay. So there's a lot of stuff here for SL, so we'll probably end up going to 11, but we'll see. Okay. Now, sorry. Questions about geometry before we move on, because now we're going to talk about polarity and IMFs and things like that. Sorry. They're just grabbing a donut. Okay. All right. So, bond polarity, okay? Bond polarity versus molecular polarity, okay? So, how to determine bond polarity and how to determine molecular polarity. We're going to kind of go through this a little quickly, but bond polarity. Yes. I would say probably about till, I would say 11. Yeah. Maybe 10:50, we'll see. Bond polarity is based on the difference in electronegativity. So, yes, Mofe. Okay. Mofe asks, is it good idea to have a sense of what the values are? I would say just to the extent of periodic trends is probably safe enough for you. So like knowing that fluorine's the highest and like francium's the lowest, that general idea is probably sufficient enough. Okay. Like I don't think on the multiple choice where you don't have it available to you, you don't have to know that F is 4 and like oxygen's like 3 or 3.5, sorry. Yes. Yes, if it's on the short answer. If it's on the multiple choice, the options will be different enough apart that you'll need. Like they'll give you like 3 non-metal bonds and then like 1 metal non-metal bond and be like, oh, that's obvious, it's ionic one. Tamor. Okay. So this idea here tells you how polar the bond is. So for example, if you have something like this, okay, because F is very polar, your bond polarity will be this way. The F pulling the shared electrons more closely to it. So it forms a partial negative and a partial positive charge in that structure. Okay? And we're only talking about bond polarity right now. We're not talking about all the C to F bonds. We're talking about just one C to F bond. Okay? And like Mofe was saying earlier, the difference in electronegativity tells you the type of bond there is. But what you have to understand is this. That number that cuts off the type of bond is not like an absolute number because books vary on that. And also, it's a spectrum of that. So, for example, like let's say you do the difference in electronegativity 0, 0.4, bless you, 1.6. Some books will say 1.7, some books will say 0.5, some books will say 0.3. Don't get fixated on the exact numbers of 0.4 and 1.6. what you want to think is that something that's very close to 0 is a nonpolar covalent bond. And somewhere in here is a polar covalent bond. And technically, this one is called ionic covalent. I know it seems kind of like a contradictory statement, but technically every bond is slightly covalent. Like even the most ionic one, there is a partially, like nothing is purely ionic. Okay, so we call it ionic covalent. Okay, now what I want you to understand is that this is a spectrum. So this is super nonpolar, less nonpolar, less nonpolar, less nonpolar, slightly polar, more polar, more polar, more polar, more polar, slightly ionic, and then up. So as you get closer to these barriers, they become more like the next one. So it's not a, oh, it stops here, it becomes polar now. It's a gradual transition between the stages. And so something that's here, something that's far left, and something that's at 0.3, the 0.3 one is still slightly polar compared to the other one. Yes, Ginevra. I I will tell you this. I don't think the IB would ever do that because depending on what source of book you read, those numbers fluctuate. So they would never do one that's right on that number. It would be solely in. It'd be like a 1.0 where there's no debate about what it would be, or there'd be like a 2.5 where there's no confusion there. That's a good question though. Okay, so being able to identify types of bonds is a general idea, not necessarily a like calculating exactly like this is 1.6, so it is slightly ionic covalent. Now, molecular polarity has to do with the overall net charge of the molecule. Okay. Now, if you have a molecule that's only 2 atoms, then the bond polarity is the same as the molecular polarity, right? Because if you only have 2 atoms, that's the whole molecule. So then there's no issue. Like if you look at I don't know, HCl, well, because the bond's polar, then the molecule's polar because there's nothing else affecting it. So this would be a polar bond and a polar molecule because there's nothing else there. The issue is when you have more than one bond, like for example in CF4. What happens here is that each of these pull in equal and opposite directions. Now, yes, I know this is not tetrahedral, but it still gets the point across. Okay? So this is slightly negative, and this is slightly negative, this is slightly negative, and this is slightly negative. But they're all the same slightly negative. So is the outside of the molecule have any net difference in charge? No. They all cancel each other out, right? So this is a non-polar molecule, but it has polar bonds. It would not dissolve in water. Correct, right? Mofe is kind of leading us to the next point we'll talk about a little bit later. Is well, in properties, yeah, with solubility. So because nonpolar, it wouldn't dissolve with polar molecules. Yes, Pancha. Yes, these represent the dipole moments of this. And you can draw an overall dipole moment as well, which we'll talk about in a second. Yes, this one? Yeah. Okay. That's it? Oh, I thought you... Okay. Now, so, yes, these lines are dipole moments. Now, what you'll see is something like this, where you have something like CH3F, where this dipole moment is much larger than any other dipole moments. So the overall molecule has a dipole moment of that way. And that's how you draw the dipole moment of the overall. So you draw an arrow, and the tail is always the positive end, and it's always pointing toward the negative end of the molecule. Sorry, I'll scroll up a little bit. Now, one note for this, okay? Lone pairs are always more negative than anything else in the structure. So lone pairs, especially for SL, they cause the molecule to be polar overall, like default. Like for SL, every time you have a lone pair in a structure, it can't be balanced, it can't be canceled out, so it will always be polar. For HL, there are times when the lone pairs can actually be canceled out with each other, which we'll talk about in shapes later on. But here, if you think about all the shapes we talked about up here, there's never a shape where you could have two lone pairs that cancel each other out. Because even in tetrahedral, the lone pairs aren't equal and opposite of each other. They're at an angle, so they don't cancel out. So you can never have a non-polar molecule with lone pairs for SL. Always. That says always. Yes, Melvin. It says always. I realized that was hard to read. So the lone pair wins the polarity of the molecule no matter what. So if there's a lone pair on the center atom, that wins polarity. Like, for example, water. Because really, water has two lone pairs, and they're kind of at an angle of each other. So really what happens is this. You don't want to draw it like this because that doesn't represent the actual shape. Well, sorry, let me clarify. If you're trying to figure out the polarity, draw it like this and don't draw it like this. But I don't think the IB would take off if you drew the water like this, but it'd be hard to differentiate. That was weird. Okay. Sorry, hold on a second. I just got a notification in my AirPod. I'm not sure if that's low in battery, or what. Okay. Yeah. It was full when I started. Okay. To the other one. Really? Okay, hold on. I gotta check this because I didn't think that was that. Wait, where do I check the battery here? Oh. Well, it's not 100. It can't be 100. That's my case. The left is 100. Why? Oh, here it is. 9. Okay, it is low. I have time. I'll charge it again when we take a break. It's been really weird on the broadcast, but whatever. Okay. So, lone pairs are the most negative always in molecular polarity. Okay. Now, briefly, molecular polarity leads us to the type of IMF that we have. Okay, I'm not going to go over this too much because I feel like we've talked about it before, but in covalent molecules, there are 3 types of IMFs. Okay, we have London dispersion forces, we have dipole-dipole, and then we have hydrogen bonding. IMFs of simple covalent molecules. When I say simple covalent molecules, I mean molecules that are independent of each other. Like a water molecule is a simple covalent molecule because you can separate out one molecule of water from a substance. Or CO2, you can separate one CO2. The things you can't separate are like diamond or graphite or silicon dioxide. Those aren't simple covalents because you can't take one molecule out of it. But these relate to the type of molecules. So in nonpolar molecules, it is the strongest. So nonpolar molecules, LDFs are the strongest. In polar molecules, dipole-dipole. And then if you have H bonded to N, O, or F, then this is the strongest. But I want you to remember that you want to compare this as similar molar masses. So this comparison of hydrogen bonding being the strongest only really works if you have similar molar masses, relatively similar, because there are some things that have hydrogen bonding that are liquid at room temperature, and then there's some things that are nonpolar that are solid at room temperature. So mass does make a significant difference. So this only really works with similar molar masses. And understand that if you have hydrogen bonding, you have the other forces as well. They're just not the strongest force present. Okay. Let's see. Okay. I guess two more things. Oh, sorry. I will scroll back down. Okay. Are we ready to go? Oh, for nonpolar molecules, this is the strongest method. For ones that have hydrogen bonding, this one's the strongest. That's what I meant. Okay. Two more things. I mean, they're not short, but there are. We still need to go over them. So the next thing is physical properties of covalent molecules. Okay. One. Okay. For simple covalent molecules, they are generally never conductive as a pure substance. I would just say never conductive, to be honest with you. Like getting into acids and bases and stuff like that is not really sufficient for what we're talking about here. So they will never be conductive, solid, liquid, or gas. They're not conductive. Okay. They can be relatively high volatility. So compared to a metallic bonding or ionic bonding, they're very volatile. They evaporate much faster at a faster rate. Okay. And the last thing that Mofe kind of intimated as well is solubility. Polar dissolves polar, and nonpolar dissolves nonpolar. We talked about this in organic chemistry, so I won't go into that too much. But a polar molecule, because it has similar attractive forces, they're able to pull apart the other species in the substance. Yeah, like assuming that's a simple covalent molecule in its purest state. Because I mean, some could argue that like if you put like HCl into water, it would be conductive because it's a strong acid. But we're talking about like just pure HCl because there's no ions or free moving electrons. Okay. The last thing for SL here, okay, is okay. I just want to double check with something because I want to see if they. I want to see something really quickly. Okay. Oh yeah, right here. Okay. The last thing we have to do is talk about giant network covalent molecules. I guess really, yeah, compounds. Okay. So there are four that you need to know. Three of them are allotropes of carbon. one of them is a compound. Okay, and so the three you need to know so an allotrope is essentially a molecule made of only one element. Okay, so the three allotropes of carbon are graphite, diamond, and fullerenes. Okay. Now, where's my structure for them? Oh, here it is. Okay. So the idea is this here. Okay. I'll leave the structure in the notes, but the things you really want to kind of focus on here are the types of bonding, the structural shape, and some of the physical properties of this. And so graphite is carbon to three other carbons. Oh, sorry, two other carbons. Whereas diamond is carbon to three other carbons. And fullerenes are C to two other carbons. Okay. That's main. That's it's all covalently bonded, but that's a main kind of characteristic. Okay. Graphite has a lone electron that allows for conductivity. So that free moving electron allows for conductivity. Wait, I'm saying this wrong. I'm an idiot. I took one carbon away. I'm sorry. I wrote it right the first time, and then for some reason I thought it was wrong. I'm off by one carbon each time. Sorry. I was like, I said three, and then I try to simplify it. But so, sorry. Graphite is carbon bonded to three other carbons. Diamond is four other carbons because it's tetrahedral. And then fullerenes are also three. I don't know why I said two. I said three, and I took one away for some reason. So carbon to three other carbons, carbon to four other carbons, carbon to three other carbons. The lone electron between the sheets of graphite allow for conductivity to be present. Okay, and these sheets are trigonal planar sheets, and one sheet is called graphene. Okay, so each sheet is called graphene here, and they're stacked on top of each other with weak LDS. Yes. So it's a flat sheet, and all the carbons are trigonal planar of each other, the Ys. Diamond has no free electrons, so no conductivity, and it is forming a tetrahedral shape. Okay. And fullerenes really you want to focus on is you have a free electron, and that there are 12 pentagons and 20 hexagons. Yes. I guess they could ask you to sketch it out kind of very generically, but I think they're going to more likely ask you to describe it. Yeah. Okay. If you really want to know the name of the fullerene, it's called a truncated icosahedron, but you don't need to write that down. Yeah, it's C60. Okay. Yeah. It's all hexagons. Oh, yeah, sure. Yeah, if you look closely here, you can see the hexagonal sheets here for that. Okay. Yes. I I'm hearing like the IB doesn't explicitly state. Like I would think that because the issue with that is although the electron's free flowing, a fullerene is an independent molecule of itself. So like I don't think the electrons jump from one fullerene to another, so I don't think it's that conductive. But with graphene, because the electrons are moving between sheets, they can actually jump across different spaces. So I don't think they're as conductive. Maria. Okay. Yeah. Well, because it is an actual molecule consisting of 60 carbons. So it turns out that 60 carbons is the ideal number of carbons that a graphene sheet, but it's still not exactly a graphene sheet because there are pentagons distributed throughout. So you have to add pentagons to create that entire spherical shape. Yes, but a, a C60 fullerene is that. A fullerene tube, a nanotube, has all hexagons and then pentagons on the ends if you encapsulate them. Yeah, if you want to. Yes, you can encapsulate it. Okay, last thing. SiO2, silicon dioxide. Now, the reason why silicon dioxide is important is twofold. Okay, one, it is a giant network covalent solid. But two, silicon is in the same group as carbon. So you would think it would bond the same way carbon does, double bonds to oxygen, but it doesn't because it's a network covalent. So what actually happens is that silicon bonds like this, where instead of two double bonds, it has four carbon to oxygen. I'm sorry, not carbon. I almost said that. Silicon to oxygen single bonds. So the IB likes to take advantage of that because if you don't know SiO2 and you just look at the structure, you would think it would bond the same way as CO2, but it doesn't. It bonds with four oxygens in this tetrahedral shape, kind of like a diamond. Okay, Marcus? CO2 bonds as a double bond to both oxygens, like we did with the structures. Oh, wait, we didn't do CO2. Oh, yeah, we did. CO2. CO2 is two double bonds. It doesn't form a network covalent. So you want to, this is a common thing, again, because if you haven't studied SiO2, you would assume it bonds like CO2, but it doesn't. And the reason, why do you think it's still called SiO2, even though each Si is bonded to four oxygens? Why is it called SiO2, even though that it's bonded to four oxygens, each Si? Look at the structure here. Tyler? You're on the right track. Yeah, the ratio is SiO2 because each oxygen is bonded to two silicons. So really, there's not four unique oxygens bonded to each silicon. Each oxygen is doing double duty with two silicons. So the ratio is really two silicons to four oxygens, which is SiO2. So you have here a tetrahedral shape. That's like diamond. So silicon to four oxygens, but each oxygen is bonded to two silicons. That's why it's SiO2 and not SiO4. But again, you want to definitely know the fact that it is four single bonds instead of two double bonds that CO2 is. Common multiple choice question, sometimes a short answer question. Because the size of the atom allows it to be able to be an independent molecule that it doesn't need to share, kind of distributed that way. Okay. Questions about that? Okay. We will take. Oh, sorry, Angela.